Hello everyone, we are starting a free open lecture in our Discord. All our lectures are held weekly without interruptions. If you wish to ask questions and receive answers, join our lectures. You can find the link to Discord in our Telegram channel. To find out the exact time and date of the upcoming lecture, make sure to join our Telegram channel for all the latest updates and notifications. So, now the most important thing to remember is to stay tuned for more information and announcements. The most delicious part of this task is absolutely right here, in this very spot. Because each and every time I open these two functions, union and join, it's incredibly hard to immediately and clearly understand what exactly is going on. So to begin with, we have the coloring of paths in profile B. What does this essentially mean actually, in essence? We look at the maximum path number that is occupied in profile A in the given context and analyze the results to understand the implications. We update it and obtain. Next, in order to carefully and meticulously number all of the transitions in the array B in ascending order, meaning everything except 0. That is, we increase the count and assign it if there is a transition in this item in the column. Specifically, we look for any changes or movements within the data set that indicate a transition. Next, we perform the actual check. This step is crucial as it helps us validate the integrity of the data. We have a counter K, which really checks something.
Want to become a great programmer? Subscribe to our Telegram channel.
We have something very interesting and exciting like this waiting for you. A cell, and we can enter it, either from the left, meaning there was a transition somewhere around here, or here, and further along, there is a path along the row, and we can enter from here, from the left, or we can enter from above, meaning a transition from above. And we can enter from the bottom, so we need to understand if there's any nonsense happening here, meaning we can't have, for example, entries coming in from 3 sides at once, because we won't be able to manage that. In other words, we end up in a situation where at one point he went there first, then came back, which means the converger breaks in this situation. We need to ensure that there are only 2 or even just 1 entry. If we have 0 entries into the current cell, it turns out to be empty and we haven't utilized it, which means we can't proceed like that. To get the truth, it is indeed clear that the rules of the combinator will definitely break accordingly. So there may be transitions either this way or that way. So what we need to do is just go straight down like this. We have the option to continue along the same path, or alternatively, we can choose to go this way, depending entirely on the specific situation we find ourselves in at that moment. This thing will now be checked using counter K. That is, we are checking for transitions equal to 0 from A, transitions from B, and transitions from left. It is being added up, the number of transitions to the current cell. If K is exactly 0 or 3, then return join, where join is by default false, meaning such a transition TFSP cannot be obtained. Furthermore, if there is exactly 1 path entering the cell, we will determine its color. The color will be such that it can immediately sum the transitions from here, here, and here, because 2 out of 3 of these colors will equal 0. Accordingly, from the summary, we will simply get the color from where we came. In the scenario where we have exactly 2 transitions, the process involves repainting one of the elements, specifically element B, to match the color of element A. This ensures consistency in the color scheme. That is, if we have a transition such that we entered somewhere like this, we have some color A here, and there will be some color B here. We absolutely need them to be painted in one color, that is, we definitely repaint B. This is very important. If we entered, that is, if left equals 0, then we have a seamless transition. Only in this case do we paint like this. Here is A and here is A. Next. If we entered from the left, we are essentially repainting what is happening here. This means we pulled it from the left somewhere, and now we are repainting what will be on the right. This is a case where, in terms of painting, we come from somewhere over here, like this or like this, and it needs to be consistent in all cases. Essentially, we are seamlessly transitioning and repainting consistently what is happening over here. In some specific cases, at the very end of the process, they had exactly the same color, and here, in this situation, we can get the value TFSP false, which essentially means that we are trying to create a cycle. That is, something like this, when we still have potential paths that may prevent us from making this cycle. This means that if something else is happening there, we do not yet have the right to create this cycle, or rather, how to put it. But we do not have to do this if we simply have either there is something here, or I definitely don't remember here. In short, the check will be whether we can do it this way or not. If we can't, then we basically cannot perform a join. It will return false. And then at the end of all these passes, if we have some approach to the right or left, from right to left, then this is also basically a join. But I think it's essentially clear why. So if we have completely gone through all these cells, we are left with one cell, and it goes somewhere to the left. And where to? If everything is already finished, we either need to turn here or here. That's why it can't be done like this. Therefore, in essence, it will be incorrect here. Next, normalization of the profile occurs. What does this mean? This means that while we were essentially recoloring B to A, the numbering system of B could be too high, meaning it could start from 1, or not from 1, but from 2, 3, or something else like that. In fact, to lower the numbering, we recolor using the passive C. Yes, exactly, we go through this. If there is a transition in the web, we increase the path number and pass K. Otherwise, we pass the color that was sent to the other end with the same color. So how does this happen? To explain further, in this process essentially, in the web transition, we increase the path number to the other end. TFSP, if we had a path with color 4 somewhere in the loot table, and there was a path with the target 4 when we entered, a maximum of 2 colors was used here. I know that we can recolor this 4 to 3, so we remembered that for the next 4, we should also recolor to 3. Consequently, when we enter here, we will automatically recolor to 3. There may still be some used amount of colors here, but in any case, we will recolor to 3. So, there are questions about the join function. What is taking place here? What is this counter? How do we normalize the profile and recolor it to the required colors? What's going on here? Jen, do you have any additional questions? Do you have any questions? Well, the counter is essentially clear in principle. Now basically let's discuss the normalization once more. Well, look, we really need to find the maturation period, the units, right? It's very important for us to avoid duplicate profiles. We have a counter and it is set to count. Initially, it is equal to 0. Then we have some profiles here. This is how they go, somewhat. And they have some kind of port numbers. Here it's 2, 2, here it's 3, 3. Essentially, the most important thing for them is that they are simply unique and have a pair. How they are numbered here doesn't really matter. Next, we are going like this, from left to right, TFSP. We encountered the first profiles. Number 2. First of all, each new profile is +1. Wonderful. Next, we will now proceed to recolor the two separate elements into a single unified one. At the same time, we also remember that if and only if the color is indeed equal to 2, it actually needs to be changed to 1. We remember this. This is done with the help of this thing. We remember that this color, which was originally, is how it should be, and this is how we pass it to the other end. Next, we move on, and once again, encounter a trio of characters, each with unique and interesting traits. We need to recolor it to the number 2. It's important to remember that if the color value is equal to 3, it should be changed and recolored to 2. For instance, imagine a scenario where you have a color-coded system, and the color 3 represents a specific state. In such a next we encounter the 2. For the 2, we have a condition. There must be a 1. Recoloring. Next, we encounter a quartet of 4 members. Our counter will then increase to 3. And we will recolor this to 3. Remember that if the encountered color is equal to 4, it needs to be changed to 3, without exception. Next, we encounter another 3, which is important. We just simply recolor it to C2 a bit more. And we will encounter a quartet. It needs to be recolored. Three is now clear, right? Right now. So there are still 2 functions left. The word but is more or less clear. But what does union do? He recolors all paths from C1 to C2, meaning that if we had some transitions, we need to ensure that here and here it is like this. He will do such a thing accordingly, so here we will have, for example, C2. Essentially, he recolors in a way that ensures consistency. In this manner, for instance, we see that C2 is achieved. In particular, here is C1, and we basically need to recolor all C1 to C2. That's it, simply. This is where the thing happens. If we encounter C1 in the array A, we recolor it to C2 in the process. Specifically, if we encounter C1 in the array B, we recolor it to C2 respectively. C2. This coloring thing is needed to find the ends of the paths and number them properly. This process is essential for ensuring that each path is correctly identified and labeled. So, this is how we get the solver for what is happening here, providing a clear understanding of the situation. Everything will already be ready for it here. The entire graph has been calculated. Accordingly, we iterate through the rows, starting from the first one, and everything is also ready for the 0. We iterate over the vertices, meaning this is our mask from 0 to 1 and from 1 to 2. This process involves checking each vertex and its connections. If we set all to 1, for example, we check if we have an edge. If it exists, we add what was counted on TFSP in the previous profile to the next one, meaning we simply store 2 strings, and this is the number of ways to obtain a profile. This ensures that we accurately track the connections and the number of ways to achieve the desired profile. By iterating over each vertex and examining its connections, we can ensure that all possible edges are accounted for. This thorough process helps in maintaining the integrity of the profile and ensures that no connections are missed. In the I1 row, this is essentially for I3 when transitioning from one state to another from I1 to I3 and when transitioning from I to I1. To continue storing only 2 arrays, we pass what was the next profile to become the previous one, and for the next, it will be 0. And then we simply sum the function f0 in the case when there is a graph, meaning there is an edge connecting two nodes. This is important because it signifies a relationship or a connection between the elements in the graph. Additionally, at the end of this process, we will press 2 because we will have a mirrored profile. This mirrored profile allows us to enter from top to bottom as well as from bottom to top, providing flexibility in our approach. We will multiply all these things here, and it turns out to be TFSP, which stands for Total Function Sum Profile. This is a crucial part of our calculation. So we have covered all the code here in detail, ensuring that every step is clear and understandable. Do you want to become a cool programmer? If so, understanding these concepts and being able to apply them is essential. Programming is not just about writing code, it's about understanding the logic and the processes behind it. By mastering these skills, you can create efficient and effective programs that solve real-world problems. So keep practicing and keep learning.
Want to become a great programmer? Subscribe to our Telegram channel.